This is the last video. So glad we had this time together. Share a laugh and sing a song. So, still with regression, and you've already done in class using R, linear model, done this before, and we said at the outset of the course that what we wanted to do is lay the foundation for someone to become an expert with data and in statistical inference and causal inference. And this course is just what has been what it's been. So we get to a point where you just have to point to things that are more sophisticated, more advanced, neater, unbelievable, and this is one, the finish, the fini. There's no epilogue to the video series. When this thing is over, I'm packing the computer and going home to Oxford. So up to now we've spoken and gone through regression where we assumed the dependent variable y is measured at the ratio level. It's a continuous measure, and just now have moved off into looking at independent variables that are nominal, broke that down in the dummy variable context, or binary, looked at that in the context of interactions and in terms of mean difference tests, and then moved everything on the left-hand side of the equation that we've been working with in the last couple of videos, and wonder what happens when you have a dependent variable that, for example, is dichotomous, like vote choice. So I'm going to think of this equation and reference a tried and true example. The example being partisan vote choice. I sort of had to be inventive to speak of the Michigan model in the multiple regression context earlier, sort of making a supposed ratio level variable for vote choice by considering certainty or uncertainty prior to the election. Let's say the election's over and each person in our sample either voted for the Democrat on the one hand or voted for the Republican on the other. That's a binary variable, and many binary variables are of interest to political scientists and other social scientists as a y, as a dependent variable. Ordinary least squares and the simple linear model won't work dependably when you specify a dependent variable that is binary or dichotomous. It actually will work. I mean, the computer's stupid. If you put in a 0, 1 dependent variable in a simple linear model, the estimation will go forward. What we find, though, is that oftentimes those models predict outside the interval of 0 and 1. That's a problem. Predicting outside the interval of 0 and 1 when the dependent variable underlying it is probability is incorrect. So probabilities are bounded by 0 and 1 in theory, and we need to, in practice, make them bounded by 0 and 1. And a generalization of the linear model allows us to do this. This is one example of many from R that are available at your fingertips and produce results that, while requiring more subtle interpretation than do those from ordinary least squares, results that look familiar. Coefficients attached to independent variables, z-scores or t-scores attached to the coefficient estimates from the independent variables, and the all-powerful p-values that indicate statistical significance given some measure of control, which is number 3. So I want to tell you about one. I want to give you a couple of names. This is kind of a cookbook approach to the finish of the class. So a test question of what would you use if your dependent variable was dichotomous? An answer would be the logit model. Logit. Or logit link function. Logit is a logistic regression. The estimation strategy is not ordinary least squares. Typically, the estimation strategy is called maximum likelihood. It's a trial and error approach. It is very powerful and much in use throughout the social sciences, the idea of the logit model. It's also called logistic regression, and the logistic regression in specific form is the logit model. The idea is going to bound the probability so that they can never go underneath 0, and on the one hand, and they can never go north of 1 on the other, which is mathematically required, right? You can't have a probability of 1.1. And this is done in a fashion that's too sophisticated to explain relative to the prep for this course. But these are very, very, very simple, easy to run, quick models, and I actually have given you the R code. Suppose you had data and you had scored up vote 0 and 1, party identification, and the customary 7-point scale. There's an ordinal level variable. This syntax is the same as you've used in class when you used R. CCE stands here for comparative candidate evaluation and should ring a bell from an earlier video. And then issues we could score up also on some ordinal or even interval ratio level measure. Now I didn't have enough room over here. You could type all this in one line. Do it very quickly. Remember, I was just saying on like a model, create a model. That's going to save the results, or keep the results, and then you can just type M after you've done this, and it'll display them. So the only thing you're adding here is the formula is binomial. So we're changing the distribution. So ordinary least squares, assuming the errors are distributed normally, and it's going to give you the wrong result with a binary or dichotomous dependent variable. So just changing the distribution. And selecting a link function, these are called. And I highly recommend logit. There's another one called probit. Logit's cool. Either one of them, rather than interpreting the coefficients in the typical unit change way, you interpret them or use them and manipulate them to generate predicted probabilities, which is pretty cool. So you move one of the x variables, for example, say a standard deviation to its right, and then you spit out a prediction and translate it into a probability. And descriptively, the way you interpret these things is to say, as I shift from, for example, on partisanship, from strong Democrat to independent, I see a change in the predicted probability of choosing the Republican of 0.2, or whatever the answer given by the guts of the model turns out to be. And there are extensions too for other kinds of variables. Imagination knows no bounds. And so technically it's inappropriate to use ordinary least squares on an ordinal dependent variable. And so guess what? There's a routine called ordered logit. And probit too. Recommend the logit. And what about the multinomial? What about the multi-category nominal variable like religion? Like choice among candidates in a partisan primary where there's no particular order. The numbers don't mean 2 more than this. They don't mean an increase of anything. Well, how about multinomial logit? Yes, that too is at the tip of your fingers, available in R and in other packages. And the logic of multinomial logit is not unlike the logic that we saw when we dummied out a multinomial variable. It was religion in a previous video, and chose a comparison category. The comparison category we chose were people who did not choose any religion, the a-religious or non-religious. And multinomial logit kind of follows the same logic. So it's more complicated mathematically and statistically, and too sophisticated on that front for us to dig into in a course like this. But I do want you to know that it's out there, so you can choose a category on a dependent variable and examine how each of the other categories relates to it probabilistically, given a set of independent variables or a set of predictors. And so the end and answer is what? basic tools, that we've gathered up in here throughout the course of the term, finishing here with linear regression and more than one X, multivariate regression, finishing more recently with some descriptions of how you can manipulate that basic model into something theoretically that fits a circumstance and empirically seems to fit the data. You could go on and on and on. There's no end to this. And using R, if you had sufficient background, you could sit down and write your own estimator. Create your own statistic. There's no end, really, except the imagination and the preparation and the background for doing this kind of work. So at the end of the day, it doesn't matter what our Y is in terms of the level of measurement. We can bring to bear some generalized form of the regression model that we've dug into in the class quite deeply, and gather up covariates, gather up independent variables, and bring about some sort of control in an observational study. Now, finishing sentence. These aren't perfect. There's not a definite answer to whether X causes Y in an observational study. There's not even a definite answer in a true experiment where there's random assignment to treatment or control. But that latter is better and provides more control and more certainty that you are observing a causal effect. This is sometimes necessary. Yes, people criticize the observational studies that include controlling or attempts to control for multiple causes at the same time, and as I've mentioned over and over, the criticisms that are directed at models that contain 10, 20, 30 X variables are dead on from a causal perspective. What we're doing here is bringing to bear the best evidence that we can find, and controlling to the extent that we can for the major forces that might confound an inference about whether one variable actually causes another. That's it. That is it. I'm closing shop. I want you to know that you would use ordered logit if you had an ordinal dependent variable, that you would use multinomial logit if you had a dependent variable measured at the nominal level. And to remember this, if you look at the output that looks remarkably familiar, coefficients will be reported, standard errors associated with the coefficients will be reported, and p-values associated with the coefficients will be reported, and you interpret them in the frequentist sense in the same way that we've learned to do. Thanks for staying with me. Bye.